Okay, so I'm going to discuss very briefly today about isomorphism between two groups. Okay, since the first session of the class has been uh, uh, based upon the examination CA3, so I'm not going to take two successive sessions. Only one session will be taken. And as I wrote in the WhatsApp group that I shall be discussing isomorphism, which is actually a function between two groups. Previously, you studied about homomorphism. So there we shall make a bit of generalization, and a homomorphism between two groups will become an isomorphism. Isomorphic structures in group theory are extremely important. Although yesterday I started ring theory, but this particular section were left out intentionally. And I think that without discussing isomorphism, uh, I cannot proceed with other topics in ring theory and in field theory. So this particular topic is very important. Meanwhile, those who have joined, please write your roll numbers in the chat box. First of all, I'm going to define what isomorphism is. So I'm going to write the definition over here. A homomorphism, small f, from a group capital G to a group capital G1 is called isomorphism. If the function f from the group G to the group G1 is a bijective function. Very simple definition, and we know the functions which are both one-to-one and onto are actually known as bijective functions. Okay, so to define isomorphism between two algebraic structures in group theory, first of all, we have to check whether the function defined is homomorphism or not. And if it is a homomorphism, then we just check whether this function is one-to-one or onto. One-to-one and onto. Both of these has to be both of these conditions have to be satisfied. If all the three conditions are satisfied, then we call the given homomorphism an isomorphism. And we know, if we can recall the definition of homomorphism between two groups, the way by which it was tested was that corresponding to the group G, we defined an operation star. Corresponding to the group G1, we defined an operation star prime. We took two elements A and B from G, and we considered their composition with respect to the operation star. Now, when we operate the function on this composition, we are supposed to get a composition of this form, where the image of A and image of B are related to one another or are composed together with respect to the composition star prime. Okay, not star ones, star prime. So that was the definition of homomorphism between two groups. Now, along with this, we need to check whether the function is one-to-one and onto. If all the three properties are satisfied, we call this function an isomorphism. So as an example, we can consider the same old example which I considered in my previous class. So here I'm going to consider my G to be the set of real number and my star to be the operation addition of real numbers, so that we know that R plus is a group under the addition operation. For G1, we are considering the set R plus the set of positive real number, and the composition operation star prime is taken to be dot, the multiplication. And we know with respect to this operation, R plus dot becomes an algebraic structure, which is a group. After that, this is my step one. Okay, so once we find two groups, then what we do, we try to define a function from one group to another. So we are going to define a function from R to R plus. Okay, and the function is defined by f of a is equal to e to the power a, which is defined for all a belonging to the domain R, or all a belonging to the set of real numbers. Clearly, this particular set is well defined. This particular function is well defined. Okay. Now, once we define a function like that, the homomorphism property, first of all, we are going to check. So in step number 3, what we are going to do, we are going to consider two elements A and B from the set of real numbers, and then we combine them together, and we get A plus B, which also belongs to R, because capital R is closed with respect to addition. Since AB belonging to R, this implies FA is equal to e to the power A, and FB is equal to e to the power B. We are now going to calculate f of A plus B. By definition of the function, we know it is e to the power A plus B, and then this can be expressed as the product of two numbers. One is e to the power A and another is e to the power B, and then we can write it as FA into FB. I did the same thing in the previous class. Still, I'm repeating because right now I'm not concerned about homomorphism only. I'm concerned about the isomorphism, and therefore I want to show you the thing in its with its complete picture. So that's why I redid this particular step for you. Now this is step number 3, and corresponding to the isomorphism, if I am talking about the isomorphism, first part has been shown. Now next we are going to check whether, no, I shouldn't write A over here, otherwise the numbers will you will think that there will be some notational ambiguities. So this is my 1 with respect to the properties that are to be shown in case of isomorphism. Now step 4, or you can say the property 2 that I'm going to check is about one-to-one property of the function. Now suppose we are choosing that for two numbers A and B, the functional value of A and the functional value of B, they are same. If it is so, then according to the definition, we can write e to the power A and e to the power B, they are same. And we know from there we can directly write A is equal to B. So this implies that the images are same. When the images are same, the pre-images are also same, which consequently says that the function f is one-to-one. In step number 4, I can consider the step 3 of showing the isomorphism between the two groups. So for this, what I can do is that I can select an element B from the set of positive real numbers, and we know then that if I can select an element like this from the set of positive real numbers, we can get an element of the form log b to the base a in the set of real number, such that when the function is operated on this element, we get this. What does it mean? It means for every B belonging to R, this particular thing holds. For every B, for every element B in the codomain, there exists an element of the form log B to the base E in the domain, so that F of this element is equal to B. And this is showing that your function F is onto R plus. The function is onto function on R plus. So from this property 1, 2, and 3, we can conclude from 1, 2, and 3, we can conclude that the given function F is isomorphism. The given function F is isomorphism, and this property of isomorphism is very important, and it is also applied in the study of graph theory. So in the next session, unit, that means the last unit of our syllabus, you will get to see that this isomorphism property between two graphs will be discussed, and that isomorphism and this isomorphism, they are actually same thing. Okay, so that is how the isomorphism is defined. And if I want to write it properly, sometimes authors like it write it in this manner, that he says that F is an isomorphism. F is an isomorphism of the group R plus onto R plus dot. Okay, so this is the thing, this is the definition, this is the example. I'm going to the next page. Now, when we get and we are able to find the isomorphism between two groups, then along with this, a property comes, and this property, we don't have to prove it, but this property is actually very important. The property says, property which I'm writing in terms of theorem, it's very important. I should have put 3 star over there. The theorem is saying that let F be an isomorphism. Let F be an isomorphism of a group capital G onto a group capital G1. Then number 1, F inverse, the inverse function which we denote by F inverse from G1 to G is an isomorphism. If you can find a function which is isomorphism, its inverse function is also an isomorphism. Second one is very important. It is saying that if F is isomorphism from a group G onto a group G1, then if G is abelian, if and only if it is both way true, G1 is also abelian. Number 3, another important property, G is cyclic. Under the condition that F is isomorphism, if G is cyclic, if and only if G1 is cyclic. Okay, and number 4, for all A belonging to G, order of A in the group G or G is same as order of FA, the image of A in the group G1. You don't have to prove this result. Okay, no need to prove this result. If you have any interest, then you can go through the proof in any book. In every book, the proof is available. But you don't have to remember the proof. But you shouldn't forget the result. Now I'm going to analyze a few situations, and you will get to know that why this isomorphism is actually, the study of isomorphism is actually very important. The basic idea behind studying isomorphism is that, suppose we have a group structure in front of us that we cannot identify its properties well. Okay, many things are there which suppose a structure is there in front of us, but we cannot say whether it is a group or not. We cannot identify its structure well. Then if somehow we are able to define a sort of isomorphism from this structure to another group, and if we can show that these two things, domain and codomains, are isomorphic to one another, then all the characteristics of the codomain will be transferred to the domain. And consequently, it may so happen, inverse case also may happen, that if there are some kind of isomorphism, then all the characteristics of domain will be transferred to the codomain. Two physical systems are very near to one another in such a way so that you can define a function from one physical system to another physical system. If you can define such a function properly, and if you can show that such a function is isomorphism, then we say that the two systems are isomorphic to one another. That means the characteristics of one system will be transferred to another, or the vice versa. By transferring, I actually mean that if we study the characteristics, it is not like that it is not like a horror movie that it is being transferred or by some other using some kind of medium, not like this. By transferring, I actually mean to say that studying one particular group will reveal the characteristic of the another group. Okay, you can study one physical system to study the another. Don't have to study the physical system individually. Okay. But here are some punchlines that you have to keep in mind. The first one is that, number one, I'm putting Roman 1 over here. These points are very important, so you note it down. A finite group can never be isomorphic. A finite group can never be isomorphic with an infinite group. As, why is it so? As there cannot exist a bijective function. There cannot exist a bijective function between such groups. The points that I'm writing over here, you have to remember these points because you can expect this as question in the online examination. Okay, this is the first point that I'm making. So suppose when I'm saying that you want to show that the two groups are isomorphic to one another, you need to construct a kind of isomorphism between the two groups. Then you have to keep in mind that both the groups are of same order, should be of same order. I mean, if both one group is finite, then another is finite. Finite can match, infinite can match, but finite will not match. So this is all about the point number one. Point number two is saying that two groups G and G1 may be of the same order. Okay, yet they may not be isomorphic. Very important property. May not be isomorphic. First characteristic of this isomorphism is saying that you can match a finite group with a finite group. You can match an infinite group with an infinite group. Now, suppose you have the finite group with you. Okay, the order of one group is n and another group's order is m. That doesn't mean that they will be isomorphic always. For example, Why is it so? I can cite an example for this. You can say it is a counter example. That suppose we are considering the group G to be S3, the symmetric group of order 3. Okay, and G1 be the group which is called Z6. Okay, so these two groups we have considered. You see, they are both finite groups of same order. Order of S3 is also 6. Order of Z6 is also 6. But you cannot say that this S3 and Z6 are isomorphic to one another. Acha, since I'm writing this point, one notation that I have to talk about is that, because since I have not talked about this notation, I am unable to use it right now. When G and G prime or G1 are isomorphic, actually we use this notation, okay, to denote that there is kind of isomorphism between them. And if not, then we write not isomorphic to G1. So here S3 and Z6 both are finite groups of same order, but S3 will not be isomorphic to Z6. Question is why? Why is it so? What is the logic? The logic is, as you know, S3 is a non-commutative group. And Z6 is commutative group. So isomorphism cannot be constructed between them because of this theorem 2, that if there is an isomorphism, one group is abelian, then other must be abelian. But here, although they have the same order, one is non-commutative group, another is commutative group. So just having the same order will not define the isomorphism between them. This is point number 2. Take the screenshot of this page. I'm going to move on to the next page. Okay. My point number 3 is that there may be two groups, capital G and G1, such that both of them are finite and commutative. Suppose we have considered two groups which are both finite and commutative. Okay. And suppose the order of the group G and order of the group G1 as they are same. Suppose both of these orders are n. Suppose. Yet, after all this, they may not be isomorphic. Now the question is why? All the conditions have been satisfied. They are finite. Both of the groups are finite. Not only finite, they are of same order and they are abelian. Then what is the problem with them? Why can't we consider why can't we construct a isomorphism between the two? So for example, suppose we are considering the group G to be Z4, and suppose our group G1 is the Klein force group. Now you see, both the groups are finite. Order of both the groups is 4. Order of Z4 is 4. Order of clan 4 is 4. Both the groups are abelian also. Clan 4, I constructed the Kelly table for clan 4's group, and there I showed you that the group is abelian, if you can recall. But yet we will not be able to form any isomorphism between the two. Why? What is the problem? What is the barrier now? Now the barrier is because Z4 is cyclic group and clan 4 is non-cyclic group. This is the barrier. Because in this theorem statement 3, it was written that if there is a kind of isomorphism between the groups, if one group is cyclic, then other must be cyclic. So all the conditions were all satisfied, but still we are not able to get the isomorphism because of this particular thing. One is cyclic and another is non-cyclic. And therefore, and so Z4 is non-isomorphic to clan 4. These results are very important for examination purpose. Remember. Next example that I'm going to consider is, suppose we have two groups, capital G and capital G1. And suppose these groups are these groups are infinite commutative group. Two infinite commutative groups are now being considered. Yet they may not be isomorphic to each other. Why? Let me show you an example. For example, I can consider the groups suppose Z plus. Z is the set of all integers, plus is the usual addition operation, and Q plus. Q is the set of rational number, plus is the usual operation of addition. Both are infinite commutative groups or infinite abelian groups. Okay? Yet they are not isomorphic. They are not isomorphic since, why? Because Z plus, this group, is a cyclic group, but Q plus is non-cyclic group. We proved this result that Q plus is non-cyclic group. Z plus is a cyclic group that I asked you to go through the proof in the book. I don't know whether you have gone through that or not, but if you have not gone through, try to find it out and go through the proof. How to show that this infinite group is a cyclic group. Okay. Another example I'm considering here is this. Two groups, G and G1, may be infinite, non-cyclic, but commutative groups. Okay, yet they may not be isomorphic. Why? For example, if I consider the group R star dot and C star dot, they are both infinite and commutative groups, and which are not, both of them are not cyclic groups, yet they are not isomorphic. They are both infinite, they are both commutative, they are both non-cyclic, but yet after all these characteristics, similar characteristics between them, R star is not isomorphic to C star because I'm writing in the next page. Take a screenshot of this. The problem is the elements, the group C star has an element I of order 4 and R star has no element of order 4. Actually, here this particular statement is being considered. Now the main what is actually happening? Yeah, it is all right if you can find sort of isomorphism between the two groups, then we are happy, because study of one group will reveal the characteristic of the other group. But it is not always possible, and there is no such general rule by which the isomorphism between two groups can be established. This particular idea is yet under, research domain. No such universal rules so far has been obtained, because every time the mathematicians give a theorem, then another mathematics community always can find till now one counter example. Okay, so therefore actually it's not always easy to find the isomorphism between the two groups. It's very difficult actually. In isomorphism, there is a theorem which is very important. Sorry, I have to write over here. There is a theorem which is very important, and this theorem is actually called first isomorphism theorem. None of the theorems which I am going to write henceforth will be proved, because we are not supposed to learn the proof. Proof is not required so far. We have to memorize this result. We have to remember this result. Okay, so this theorem is actually called the first isomorphism theorem. Let us consider a function defined from the group G to G1, and suppose this function is a homomorphism between these two groups. Okay, then the quotient group or the factor group, or factor group G slash car F. Car F you already know, because you have done the problem in the examination right now. A few minutes ago you did the thing, isn't it? I defined kernel of F in the question paper. So probably you have understood the definition. The definition is clearly written. Okay, so the kernel of F, kernel of F, this particular set, it is a set. You can say that this set is a normal subgroup of the group. If we can define a function like this, and if I can define kernel of F, then it can easily be proved that kernel of F is a normal subgroup of this group. And as it is a normal subgroup, as it can be proved that it is a normal subgroup, therefore we can actually define a quotient group of this form. So this quotient group G over car F, this group is isomorphic. This group is isomorphic to the subgroup, image of F of G1. So here is the diagram for you. Suppose we have capital G, and here is an element small a, I'm showing it. And here is your set capital G1. And we are defining a function like this from G to G1. Suppose in the codomain, this part is actually the image of F, which is nothing but that we call F of G. Okay, and there is another set, third one, which is the coset, and we call it as G over car F. The coset has, the quotient group has been formed with respect to the kernel. We can similarly define a function from this car F to the set G1. We can define this function by psi. So that what is AH? Because we know this AH is not a set. AH is actually an element. It's a set, definitely a set, but we consider this set to be the element of this quotient group, because you know the quotient group's elements are always cosets. So if I consider the element from this quotient group, this will be always, this is always be equal to the image of the element with respect to the function. That means you are selecting an element A from here. With this A, you are forming the coset, which is the member of this quotient group. So here, this AH, this coset has been formed by the element of G. Now, what this figure is showing, if you consider this coset, and if I operate a function on this coset, its image, the function's image, will be exactly equal to the image of the element A with respect to the function F. And not only this H will be is equal to car. Here the normal subgroup, actually what I have said already, it is being written in the with the notations, that normal subgroup here is actually the kernel of the function. Okay, so this much I'm going to do in my today's class. I'm stopping right over here, and the point values of the examination portal, the Google form is now open. You can see your marks over there. Okay, so I'm going to stop recording, and we are again going to meet in the next week with further discussion on these topics. So till then, bye.